Okay, so the second speaker today is Alexandros Beskos, who's going to talk on closed form density expansion policy.
Okay, thank you very much for the invitation. It's nice that Yorgos spoke about SDEs. I think this would save me quite some time. So let's see. This is joint work with Yuga. In fact, Yuga did probably all of the work, to be honest. And this is based on some draft that we are hoping to have out there very recently. Okay, so let's see what this thing is about. So this is another way to write an SDE in general dimensions. So I have d Brownian motions here. So there is this thing called the drift of the stochastic differential equation. This part that in Yorgos' talk was maybe non-elliptic or stuff like that. Here, in fact, in our case, we have strong conditions on these functions. We have a different interest in our case. And then there are these things, the diffusion coefficients, right? And so there are d Brownian motions that drive the randomness of the system, but the dimension of the process itself might be larger than the dimension of the Brownian motion. So this is important for what we are contributing here. Let's see. So this is what I just said. If you put these functions together, this is the thing that is typically called the diffusion coefficient, right, in the literature. And we are aiming for obtaining a closed form expansion of the transition density of the SDE. So there is this class of models which is defined in infinitesimally small time increments. All right, so it's defined in continuous time, and it creates this problematic situation where if you want to see what happens in a finite time, we don't have explicit expressions for transition densities and things like this. So this transition density is typically unknown, apart from some trivial cases. And there has been a lot of work in getting, in trying to get some closed form expressions for this, for such a transition density. And so our focus, our interest in what I'm going to be showing is the case of a subclass of stochastic differential equations, which come under the name of hypo-elliptic SDEs. All right. So this is the case where this n there, so this guy here, so this guy here is in fact strictly larger than d. So we have more dimensions than the amount of noise in our system. These are called hypo-elliptic SDEs, and they have found applications in many different fields out there, in applied mathematics, in physics, in finance, so lots of areas. So there's a gap somewhere there because a lot of results that people have obtained for stochastic differential equations, they usually involve what we call the elliptic SDEs. Elliptic SDEs would refer to the case that the diffusion coefficient is invertible. All right, so it doesn't have we don't have this degeneracy issue. Hypo-elliptic SDEs is the case where we have this degeneracy issue. So we have an expression about the veta zeros, the VJs, and somehow we have to use these functions in the definition of the stochastic differential equation. We have to use them in a particular way to come up with an approximation of the transition density of the stochastic differential equation. All right, yes, so there's this delta here that it will appear a number of times. So CF stands for closed form, and yeah, that's it pretty much. Okay, this is what I have just said. So that's the diffusion coefficient. Lots of, in many papers about SDEs out there, this is assumed to be well behaved. Okay, this is assumed to be invertible. In many other cases of interest, So this guy is degenerate, okay? Once you are in a situation that the Brownian motions that drive the that get the noise into the system, the number of Brownian motions, they are smaller than the dimension of the state space, you are in this situation. Okay, and this is one can in general write the SDE like this to emphasize the presence maybe of some components that they are smooth. All right, so okay, maybe I have an SDE that it's made of, there's a clear distinction between some components which are smooth, and when I say smooth, I mean differentiable, right? In general, stochastic differential equations which are in the elliptic class, they are not differentiable, right? They are not smooth. Their sample paths are not smooth, so this would correspond to these coordinates of my SDE. And then here in the hypo-elliptic case, you also have some smooth components because there is a derivative here that doesn't get noise, all right? So the derivative actually exists. So there are a number of coordinates for which the sample paths, they are at least once differentiable. All right, and again, the interest here is that we are dealing with a non-linear system. We don't have the transition density, as for instance it was the case in Yorgos talk. Maybe they came from a different direction, but again they were interested in non-linear SDEs. So we want to say something about the transition density of these things. Okay, we know what happens in continuous time. We want to say something about what happens in finite time periods. All right, that's the context. So let's see. So this has been there has been a long literature that has looked at this problem, and I'm pointing to some directions here which are all for the elliptic case. So all the coordinates, they are non-differentiable, right? You don't have smooth and rough components. All of them, they are rough, okay? So we don't have, we have the elliptic case. All the works out there have been in the elliptic case. So there was a very influential paper by Aitzahaya, and he obtained a closed form expansion using something called the Hermite series. And in the context of elliptic SDEs, indeed, this paper came up with an expression that looks like this. So the transition density of interest on a finite time period of length delta, it was expressed like that for some correction term that it was analytically available, all right? So this is approximately equal, all right? So there's no, there is some error here. So some more comment here is that there is the way these expansions work is that they are somehow centered around the baseline Siebel transition density. So there is this thing that comes from a nonlinear SDE, and usually there is something which is simple times some correction. Okay, so they look like this, these expansions. And typically this guy comes from a Gaussian distribution. And then there are some correction terms that you try to use to get closer to the true transition density. And another thing that it is important here is how analytical are these contributions, all right? So what it is, whether these contributions had some result about the size of the residual term and stuff like that. So here, for instance, in this work, there was some sort of qualitative result that said that, all right, I have some expansion here, some sort of sum over some terms. The sum was going from 1 up to capital J, and there was some sort of qualitative convergence result that it was saying that as you get more and more terms in your expansion, you arrive at the limit, right? Under conditions, you arrive at the true transition density. It was not. It is a minimal type of result that one can get, all right? You don't actually say something extremely particular about the size of the remainder. It's mostly qualitative. You say, all right, as this thing, as you get more and more terms, you approach the correct thing. Okay, so it's a minimal type of requirement. Then this guy came up with another paper that he treated a bigger class of multivariate SDEs. There is something that it is called there's a class of SDEs that comes under the name of reducible SDEs. Reducible SDEs are the ones for which you can apply one transformation, and you can change them into an SDE with a unit diffusion coefficient, right? So the previous contribution was essentially for reducible type of stochastic differential equation of SDEs. Then there was another paper that the same author published, where there was an extension on a more general class of stochastic differential equation. But it came it's a bit complicated, this paper, and it came again there were not that many theoretical results, let's say, there to say, okay, so how fast is the convergence or stuff like that, okay. So the theory was not very analytical. Okay, I think this is the third of the thing I want to mention from the literature. There are some people that they use something called Maliavin calculus to get expressions like this, and indeed they produce results that they are quite analytical. So they produce, for instance, something like this. So this is the unknown thing that we are targeting. This is the baseline, typical Gaussian in Y. And then there is an expansion, and then here is the remainder term. And indeed, they did a lot of effort in this paper to control the remainder term and say that, okay, so if you include that many terms, the error that you are committing is that big in delta, right? So, okay, that's a very good effort. Here it's still in the elliptic setting, it's still in the setting that we have a diffusion coefficient which is invertible, it is positive definite. And the last thing here, it's some recent paper from 2019, and there is, I don't mention many details here. They play around with some Ito expansions with the Ito formula to generate an approximation of the true transition density. In some sense, this is closely related to the approach that we are taking in our contribution. And okay, so here I say some general stuff. It's still this previous paper I was mentioning. It was still in the context of elliptic SDEs. So we are still there's still not that much literature out there. There was no literature, in fact, out there for hypo-elliptic SDEs. And I'm just setting up the context here. I'm saying that, okay, so I will, we are interested in contributions that give expansions which are somehow validated. So there is an analytical characterization of what you are missing, right? So you say, all right, an approximation of my unknown transition density is this, and I have a remainder term that I have not included, which is of this size. Okay, so it's good to have such an analytical result. It makes someone feel better and more confident about what is going on out there. Okay, all right. So let's see. So here we are. I think the approach I'm going to take is it's very analytical. So I could have hidden a lot of the things that I'm going to show behind some proof, but I found it interesting to show that it's nothing too complicated. So let's see how this thing goes. So this is how the expansion will look like. So I'm considering both elliptic and hypo-elliptic SDEs, all right? And the expansion will look like this. This is a baseline measure. So when you are in the context that you want to include hypo-elliptic SDEs, you have to be a little bit careful about which baseline measure you use, because it has to be well defined. Also for the case of this degenerate case of hypo-elliptic SDEs. So one way to build up an approximation for hypo-elliptic SDEs is not, for instance, to use the Euler scheme, because that will lead to a degenerate transition density, but you use something called the LDL scheme. So this LDL stands for local drift linearization. So this means that pretty much you take your nonlinear drift and you apply a first order Taylor expansion around your current position x, all right? So this is why you see the derivative here of the drift around the current position x. This is this guy here, and then there is some difference there between the true drift and at the current position, and this derivative appearing here, okay? But these are now pinned at the current position, so they are constants. And then this is also pinned at the current position, so this is also constant, okay? So the nonlinear SD is approximated by a linear SD, and this has a transition density which is well defined both for elliptic and hypo-elliptic SDs, all right? So there is somehow randomness propagates everywhere. It goes in the smooth components, it goes in the rough components, it propagates everywhere. And at a finite time period, any finite time period gives enough time from the noise from a single Brownian motion. Let's say if you have dimension 2 to go to both coordinates, okay? There's enough randomness to propagate to both coordinates if we did have 2 coordinates. All right, okay, so this could be our baseline reference measure, and it remains to see what is this guy here. So here I'm just giving the analytical expression for this thing. It's just a linear stochastic differential equation. So it's a Gaussian distribution in Y with some mean and some variance that they have some particular expression, right? So it's like an Ornstein-Uhlenbeck process. At the end of the day, nothing difficult. It's a bit something which is slightly interesting is that so even if this guy is degenerate, this integral here is in fact it's a positive definite matrix, right? So you have a well-defined non-degenerate distribution. So this can be whatever, but through this operation, you get a covariance matrix, which is in fact positive definite. All right, so
you linearize the drift and you freeze the diffusion coefficient at a constant.
Yes, exactly, yes. All right, so something that a small trick that people use when they are working in this setting is this thing here. There's a third process that they define that somehow it separates the starting position from the value at which you fix these components here. So you fix at the constant values at which you fix the diffusion coefficient and the elements of the drift. There is a reason why this thing happens, and this reason will become obvious once we start to see how this program of getting the expansion for the transition density develops. All right, let's see. So if this z was equal to x, we are getting this LDL, all right? This linear approximation, this linear SD, which approximates the correct SD. And then I'm setting up some notation here. So there is this, this is for this funny process where I have pinned the drift values at some z which is different than x, the starting value. And this has a generator. So now generators will start appearing in the developments because mainly because of the fact that they are available. Generators look at something that happens in continuous time. In continuous time, we know everything about the stochastic differential equation of interest, so we have analytical expressions about these guys. So we know the generator of this process, we have an explicit expression about it, okay? So this guy, calligraphic L and 0, z as a superscript, this guy is available. All right, it involves continuous time. All right, but we have to go from continuous time to discrete time. So what is the process of doing that? Before I show the steps for going from continuous time to discrete time, another definition, this is the generator of the SDE of interest itself. Again, because the generator refers to something that happens in continuous time, it's something that we know we have it, right? So the calligraphic L, we have it. There's no problem with it, okay? And another thing that will play a role is the difference between these two things. They are supposed to be close, these two generators, and they give rise to this L tilde thing, which is the difference between the two things, okay? The generator of the correct SDE minus the generator of the linearization of the SDE with this funny allowance, so with this funny extra flexibility that we pin the drift and the diffusion coefficient at some constant value which is different than the starting value. All right, how do we go from things that happen in continuous time to things that happen in finite time, okay? To things that happen at a period of size delta. In fact, this is not that difficult, so there's nothing too strange here. This is why I have decided to show the steps. So, to show the steps in some detail. So, all right. So we need somehow to connect these two things, right? That's the true quantity we are interested in. That comes from this linear SDE for which we know the transition density, right? And somehow we have to connect these things. There is some standard result from calculus that says that okay, this guy evaluated at 0, so this would disappear. So at 0, this guy is equal to the unknown quantity. This guy at delta is equal to the at 0, this guy is equal to the known quantity, and this guy at delta or at t here is equal to the unknown quantity, right? So very standard result from calculus is that g evaluated at t minus g evaluated at 0, it is equal to this thing, okay? So now the expansion, this is the first step of where we start building up this expansion, right? And in the sense that we say, all right, this guy here, the unknown quantity is equal to the known quantity plus this guy here, okay? Let's see now, so what are the tools that we use now from the theory of stochastic differential equations? Well, nothing more than Kolmogorov's backward-forward equations. So there is some understanding about what is happening to derivatives of the transition densities with respect to time. So if this is what we need here, so imagine we need the derivative of this with respect to s, that if you take the derivative here with respect to s, it will go inside the integral, and it will involve the derivative of this guy here, of the one factor, and then of the other factor, all right? Derivatives of transition densities with respect to s, there's a very famous expression coming from these Kolmogorov's backward-forward equations that involves again the generator of the process, right? So, and it applies either in the backward sense with the generator itself, or it applies in the forward sense with the adjoint of the generator. Okay. All right. The same thing happens for the same thing applies for this linear stochastic differential equation. It's either the forward, the backward derivation, or the forward one. Right. Okay. So this is this very standard quite standard result from the theory of stochastic differential equations is what we are going to use to learn the derivative of this, right? And then we will take integral and start building up on this expression, all right? Okay, so let's take the derivative. So with respect to the time s, the derivative goes inside the integral. So remember, there was the derivative of this guy with respect to time. This is why this generator appeared here. They are joined, all right, because that's derivative. That's the case of the forward Kolmogorov's forward equation. This is the case of the Kolmogorov backward equation. That's the derivative of this guy with respect to time. And then the only thing that happens from here to here is that we have switched the adjoint. A standard property of the adjoint is that when you have an integral like this, which is a multiplication of two things, you can switch the position of the adjoint and change it with the operator itself, all right? So here we are. So we have actually the difference of the two operators. So we get something like this. We get this expression here, okay? This P, this capital P with subscript s, is the transition operator, let's say, all right? So applied on a test function phi. So the test function phi here being exactly the difference between the two things, okay? So I have replaced the integral with this guy here. It's just a definition, essentially, okay? I'm just working with the definition of the transition operator. All right, so things start looking promising. So now I know that my true transition density is equal to the approximate transition density plus this thing, okay? And now it's time for an iterative application of this thing. So I know, again, I repeat what I have just said. So I know that this guy here, which is pretty much the transition density of my SDE, is equal to the transition density of a linear SDE plus something plus something extra. Okay, so let's see what I mean by that. So this is I'm just stating the result that I have already derived here in a formal way. So that's one of the lemmas in the paper. And now what is going to happen next is that this guy now again, so this equation is going to be used repeatedly. So this guy here is going to be replaced with this plus another iteration of this, all right? So somehow this integral is going to grow and grow in size. So this is what I mean. I'm showing that here in detail. So this was what it was stated in the lemma. And then this guy here on its own, but evaluated now at S1, is equal to the corresponding transition operator of the linear SDE plus this guy here, okay? So if you imagine what happens here, and then this guy here will be replaced again with the P bar plus some extra components of this form. If you imagine what happens here, there will be a sum of such terms. So it is this guy here. It is this term here plus some residual term. All right. So this is where we are. So the things are building up slowly. So we have come a long way already. So the expansion keeps developing. So this is the unknown quantity. It is equal to this plus this. And this guy involves only the generators. That's the difference of the generators, plus the transition density of the linear SD. So this guy is explicit. All right. So we know this guy here. It doesn't involve this operator. This operator goes inside the remainder term. All right. This thing here is now analytically tractable. And that's pretty much the idea, to be honest. I'll make some comments once I show the final formula versus other approaches that people take in the literature, and why it is that this approach seems the most promising to me for hypo-elliptic SDs. All right, so if we want to be precise, so there are each of these terms is analytically tractable, and in fact it is equal to some many integrals with respect to time of this hat guy that involves all these operators, operator. But these guys, they are all available. All right. There's nothing here in calligraphic T hat that involves the nonlinear SDE. There is something that involves the linear SDE, but it is inside this generator. And this thing, we have it, all right? We have the generator of the nonlinear SDE. But for things that involve finite time, everything comes from the linear approximation of this SDE. All right, so we work with something that we know we should be able to get some expression for it. And we have to do some work to manage to get there. So let's see, so how do we get a nice little expression for these guys here? And then after we get this expression, we have to take the integrals with respect to these components here, blah, blah, blah. There is still some work here to be done. All right, so we need some definitions. There is this thing called the commutator in the SDE literature again. So it is defined like this. So you have two operators, two differential operators, and this bracket process is defined like this. All right, and you can define an iterative process where you apply this guy at the bottom. You apply it once in this bracket operation. You apply it twice, etc. You can apply it many times, and we give a name to this. So somehow, this quantity will appear somewhere there. In the derivations. All right, okay, so let's see what is happening here. So we are looking at this guy, and that's the simplest case. In fact, that's a small version of this iterative procedure, and we want to get a feeling about we want to get a nice expression that we can play around with. For this quantity, all right. So let's see. So apparently the way to do that is to use a Taylor expansion of this quantity around 0. So we look at the time component, and we expand it around s equal to 0. So around this, we do a Taylor expansion around this variable here, around this coordinate. So it so happens that nicely, okay, again there is, I'm looking at this term, which is equal to this, because here I'm using the analytical definition of the transition operator of the linear scheme. So it's the expected value of this function according to this transition density. And I will take derivative with respect to s. There will be, the derivative will go again inside. There will be a derivative with respect to s. So it's again a use of the Kolmogorov backward and forward equations, which will have an impact. So here I'm taking the derivative with respect to this guy. I'm taking the derivative with respect to this guy here. Kolmogorov forward and backward equations are used again. And it so happens that I get exactly this bracket operation. So I get the product of two operators. This in fact will go, this is the adjoint. It can move here. It can go on the other side of the calculation and change to the regular operator, not the adjoint. So there is a product of two operators. So A times B minus B times A. That was exactly the definition of a bracket between two operators. So it's exactly this thing here. So now it's not difficult to recognize that this is the function itself, G. But now instead of having this operator at the top, there is this guy at the top. So just to show here what I mean, with this guy at the top, it had this in the middle. And now yes, so let me be more specific. So with this guy at the top, it had this guy here, all right? And these two transition densities. And now it's exactly the same thing, but these two transition densities are the same as in the previous slide. But now there is this operator that applies on the left, all right? So it's the same thing, but now it's this operation. All right, there is an iterative process anyway. If you get now the second derivative, this guy here will apply another more time on this operator from the left, and then another time, and then another time, and another time. So this is why this commutator, it was of some use, because once you apply lots of derivatives, you get this guy applying to this operator, applying to this many times from the left. All right, so here we are, and in particular in the Taylor expansion, we are interested in what happens when S is equal to 0. This guy disappears, and we get something like this. Okay. So we have a Taylor expansion. So we have a Taylor expansion of a function that, let's see where we are. So this, let's see, I forgot myself where we were. So this is where we were, and let's go even farther back. So this is where we were. We were building up on this expression. We had this guy, and we said, look, this guy, in fact, by doing some iterative calculation, it will give us lots of these guys, and each of these guys it involves many applications repeatedly of this operation. All right, and now we have obtained a nice simple expression of this guy here, of this operator. All right, so this is what we have achieved, and this is what we are going to use now. Yeah, this was the operator in the expression we have, and we have Taylor expanded it. Okay, let's see. So where we are now. All right, so we have Taylor expanded it, and we obtain this. Okay, and sometimes somewhere at the end of this expansion, there is the transition density itself. But anyway, this doesn't change that much. It's like the transition operator, but you just have the identity at the identity function for phi. It's not that different, the result. And we are about to summarize where we are. So this is what we have achieved, and I repeat again of what I have just shown. For this guy here, we have obtained some Taylor expansion, and we are going to plug in the Taylor expansion in this formula here. Okay, we will get the Taylor expansion in this formula, and this is what we will get. So we will get something like this. So once we use the Taylor expansion, there are some multiplications of generators. when I say multiplications, I mean essentially compositions, all right? So the one operator applies, then another operator applies, then another operator applies, etc., etc. So we get an expression like that at the end of the day, plus some remainder. These are now, here it's a matter of, it's not a matter of doing something super complicated. It's a matter of being careful with the calculations. So we multiply a number of Taylor expansions. So these multi-indices will appear there. So this is a number of integers of a number of j positive integers. So these multi-indices appear in the expressions. And then, whoop, this is the thing that comes out of all this effort, which is a composition of the various operators we have there. Okay, all of these guys are tractable, all right? So this is the differences between the true and the linear approximation. This is simply the generator of the linear approximation. So this guy is tractable. So let's see where it is that we have arrived. Some definitions here that I'm just using them so that some terms I'm giving later on, they make sense. So this is where we have arrived. So we actually take the integrals now with respect to time. They are not difficult. So we get some things that look like this. What's the point at which we are now? So we have reached the point that we are saying that the true transition density is equal to the transition density of the linear SDE plus this thing here. And this doesn't look that complicated somehow. So there are some powers of delta at the end of the day. Delta is involved here, and there is this guy applying on the transition density. So maybe there are some powers of delta also hidden in this term. So the last thing that is a little bit involved is that we have to make some effort to see which powers of delta they are controlling this term. But please notice that again, all these quantities here, they involve explicit things, okay? So this is again the transition density of the linear SDE that approximates the true SDE. So everything is analytically tractable. So hopefully there's a good chance that we will get something that looks nice out of this thing. All right, and this is a differential operator, so there will be some derivatives of this thing. And this is a normal distribution with some variance that it's proportional to delta. So it's not as strange as it seems, this expression. All right, so at the end of the day, we are differentiating with respect to the first component. Something that I should say here is that this is exactly the point where this introduction of the auxiliary process makes a difference. The way this thing has been developed, we need derivatives with respect to the first argument of the transition density. Now, if we have worked simply with the LDL scheme, the SDE, which is a linear approximation of the true SDE, and X would appear in the drift of this SDE, it would appear in the diffusion coefficient, and taking derivatives with respect to such an X would have been a nightmare. Now, the fact that we have separated the X and we have fixed the drift and the diffusion coefficient something else rather than the initial position, it makes life extremely easier. And what we gain is that we do all these differentiations in something which it is much simpler than if we hadn't considered this auxiliary SDE. And then at the end, once we have taken the derivatives and everything, at the end we set z equal to x, right? So it's a trick that it is extremely useful. Otherwise, all this paper would have been impossible to write, to be honest. And yes, and here this guy depends on. So there is a result that we have in the paper that says that if you push this multi-index far enough, you have a remainder that it is of some desirable, let's say, size. Okay. All right. Let's see. So that's the expansion. I'm just rewriting the expression from the previous slide. So that will be my expansion, but it's still not there because there are some powers of delta coming out of the differentiation of the transition density of the linear scheme. Okay, at least I'm in this context where I have separated z from x, and that makes life extremely easier. So there is, I don't have that much time, but there is some way. At the end of the day, there is some result here that says, you know what? It's a matter of some particular derivatives of some sort. So one has to keep count of the derivatives, that all the possible derivatives, that they give a particular power of delta. So this is what it says here. And I have to find these derivatives, and we can do it, all right? So it can be done. This is the transition density of the linear SDE. So we can get which power of delta is hidden behind this expression of the derivative, all right? And it's different depending on whether you have an elliptic SDE or a hypo-elliptic SDE. So there is a separation here. All right, so once we have discovered which powers of delta are hidden here, we can get an expression that looks exactly like this. That's our closed form expansion. This is analytically tractable. This is analytically tractable, and that's the residual. And we have made a lot of effort. There's a lot of effort. Yuga, in fact, has made a lot of effort to control this residual here, to say something about what is the size of this residual. I mean, what you expect to get here is that the idea here is that there are some powers of delta. This is supposed to be an order 1 term. So hopefully one should be able to prove that this is a term, this residual thing is a term which is of size delta to the power of j plus 1 over 2, all right? So that's something that it involves a lot of pages in the paper. Okay, this is what I have just said, and that's it. That's the paper. That's the contribution, sorry. And yes, there are some more stuff here about what is exactly the way we control the residual, and the way we control the remainder, and the way we control these coefficients. I think the bottom line from here is that these coefficients are of order 1, and exactly that this remainder term is of order j plus 1 over 2. I won't dwell on this. There are here the conditions. There are some strong conditions associated with these results. So to get this control on the remainder, etc., to get this expansion, there are some assumptions on the drift and the diffusion coefficients, which are relatively strict, but that's life. Before I show the applications for 2 minutes, one comment I will make here is that we took this direction because if you forget these several calculations, at the end of the day, we just work with standard tools from the theory of stochastic differential equations. We haven't used something more than the Kolmogorov backward and forward equations, the generators of the SDEs. And that's pretty much it, right? The Taylor expansion, what else was there? That's it. So there was nothing super strange. Other approaches used for elliptic SDEs, they are much more complicated. So they involve Maliavin calculus, some difficult things that it would have been it would have led to a path which would have been much more difficult to work with, right? So somehow this approach seemed to be the most most promising, and this is why we took this approach. Okay, there's an example here. This is if you ever use hypo-elliptic SDEs, you will probably make use of this model. This Fujinagumo model. Everybody's using this example when they look at hypo-elliptic SDEs. There is an unknown parameter. Usually, in all these type of hypo-elliptic models, people observe the smooth component. All right. In physics, for instance, you have the location, and then you have that is smooth, and then the velocity that it gets the noise. So we are here, and yeah, I have some results here, which I have 2 minutes to show. That's the true SDE for some particular choice of x, some particular choice of delta, some particular choice of theta. Theta appears for the first time in these slides, but it's the same thing as we have pretty much assumed here that the parameter space is compact, so it doesn't really change the results that I have shown in the expansion. And yeah, that's the truth. And if you use the expansion for j equal to 0, which is in this case, it's simply to use the approximation of the SDE through the the linear stochastic differential equation, you get this difference. So that's what I'm showing here is the error, right? The absolute value of the difference between the true thing and the approximate thing. And here there is some difference, so this go up to 27. If you start using more terms in your expansion for the transition density, you get, so here I'm using 5 terms, you get a very small error. And last thing I would mention for the 1 minute that I have left is that people want to use methods to have a flexibility of if you are doing parameter inference, you want to have some flexibility over the methods to use. You want to be able, for instance, sometimes to be able to sample from the transition density that you are using. And it seems in this case that this is a super complicated transition density, and you cannot do that. You cannot use particle MCMC, for instance, if you observe the process with noise or stuff like that. But in fact, it's not a problem. So you can plug in this term in the likelihood and work with this and work with samples from this term. All right, so there's a simple way to avoid this thing. This is what I'm saying here. So you can put this thing you can separate this thing and use the weight in your likelihood, right? And you can do particle MCMC, you can do non-centering MCMC and stuff like that. And the last trick is that, so what happens if the weight is negative? There is a standard trick that people use that involves exponentiating and taking the logarithm and expanding a little bit the logarithm. So for instance, if you have a term like this, and you haven't included terms of delta to the power of 3/2, it's enough to expand the logarithm up to second order, because then you are getting a weight that it also loses just powers of 3/2 as this weight does, right? So you might as well use this weight instead of this. They both miss the same a term of similar size, and this guy is positive, right? So there's not really a problem there. And that's it. Yes, I think, yeah, I have mentioned some things, and I can stop here. Thank you very much.
Okay, actually, we don't know some references I went to look at.
Mm-hmm.
For instance, like so you said that the approach was like going through PDE, and I checked because I was wondering. I'm not so familiar in which case it can be this one, but for finding explicit transition densities, for instance, one method could be going through spectral theory, so looking at the generator, see if the generator is self-adjoint with respect to some measuring case, and then trying to use a spectral theory. This might give an expansion. So I couldn't find, it doesn't seem that they use this method.
Yes, someone from applied math was telling me exactly something like this. I'm not familiar with this approach, to be honest. I haven't seen it in in some paper where the interest is in statistical inference. Apparently, there are approaches like this out there. Yes, I'm not particularly familiar with these approaches. Yes. A major thing in all these things is to also come up with a way to control these remainder terms, to say that they are of this and this size. So yes, it's something that I guess someone can try with this approach that you are mentioning, just to work directly with a generator and try to get there. Yes. Mm-hmm. Yes. Yeah. Yeah. Yes. I mean, myself, I'm from a statistics background, right? So the interest here is to then have some data and have some unknown parameters and estimate the parameters. Yes.
You had this parameter Z that you could freely choose.
Yes.
It seemed that you were always taking it to be equal to X.
Yes, because you couldn't freely choose it, right? Because this process only made sense as an approximation of the true process.
Yeah.
If Z was equal to X, it just.
You can generalize it to whatever you want.
No. It's just what is useful, extremely useful here, is that there are all these operators that they come from the use of the Kolmogorov equations, that they involve applying derivatives on the starting position, all right? So if you don't separate the starting position from this Z, then you would have to apply such derivatives also in the drift function, in the diffusion coefficient, and then the calculations would become very strange. So now somehow one switches the order of the two things. So first you separate, you apply only on the initial condition these derivatives, and after you have applied, you set Z equal to X. So it's a small trick that makes. It's like a dumb variable that it helps a lot. You switch the order of two operations, it makes a difference, yes. There are conditions, there are many assumptions here, right? So all the diffusion coefficient functions, they have to be bounded, for instance. Yes, there are quite a few conditions. Yes, interestingly, so we have tried to avoid the super strong condition on the drift, related also to what Yorgos was saying. So we don't actually assume linear growth on the drift condition, on the drift function, so the drift doesn't have to be bounded and things like this. So for the drift, at least, we don't have strong conditions. For the diffusion coefficient functions, they have to be bounded, yes, in absolute value.
Do you have a rough estimate on the scaling of how long it takes you to actually build the expansion in terms of ND and J?
No, this is not expensive actually. So Yuga has done symbolic calculations with these things, so that they don't grow. I mean, I cannot give the cost with respect to dimension but I would think you have to find so things should be linear in the dimension, for instance. I don't expect things to be.
I would think it would be like D to the J.
Ah, with J as well. Yes. No, sorry. Yes, and then linear also in J. Yes. I mean, the idea here in all these methods is that typically you don't need J to be large. But with up to 3 or 4, you get some non-linearities there.
And one thing which I don't know if it's useful, but in a way with what you're doing, if you were worried about the growth of the coefficients, it might be that you could do a change of variables, apply your method, and then do a change of variables back.
Yes, yes,
So it
yes.
fixes that mistake.
Yes, possibly, yes, yes, yes. Yeah, yes, yes, thanks, yes. Thank you very much.